I'm Jeff Fried. I am co-presenting with a gentleman, Dirk Van Hilft, who could not be here. And if you were here last year, I was speaking about auto-classification. It was also a time that I was saying goodbye to people because I left this field and joined a new company called Intersystems that focuses on database and data management for healthcare. Lo and behold, I arrived there and we have acquired a text analytics firm called I-Know. So hi, I'm back. And I'm going to take off from where Brian left you and describe a particular approach to entity recognition and entity extraction that came from this acquisition called I-Know that Intersystems did. And because I've just been sort of evaluating what's different, I'll be able to show you some comparative evaluation, et cetera. And this is all incorporated now into a commercial product called Intersystems Iris. If you want to know more, come grab me at a break. Brian already talked about the basic named entity recognition or concept recognition. I'll be going through a approach which I think is a bit different and showing you how it compares. And then I picked 6 example applications. Now, anybody here a doctor or from a medical field? Great. So you can probably, you know much more than I do about this domain. I'm loving this because it's really seeing things that matter in improving healthcare in general. But this example of a snippet, which is a doctor visit note in an electronic health record system, is the kind of data that we're working with all the time. And it's data that matters a lot, is text-rich, has a lot of jargon, and is really, really ripe for this kind of named entity recognition. Now, Brian already took you through a bunch of different approaches. The Stanford NER stuff, which I've used twice in my long checkered career, including at my last company at BA Insight, is very solid. It's probably the most popular element. It uses, of course, both morphological and statistical techniques using support vector machines, and it uses this sort of 2-phase find and resolve entities in a set of known classes. Who has used this Stanford NER in the room? Okay, a lot of you have. Has anybody built new classes and trained new classes from it? Okay. So even though this is great and you'd think almost commodity, here's an open source library that works pretty well, has reasonably high accuracy, so why do anything else? From my perspective, first of all, having been involved in a lot of addition of classes, it's a pain. It's very cumbersome, it requires specialized expertise, and therefore if you're in a new domain or even a new subdomain, you have a whole process of upfront training, creating dictionaries, et cetera. And also then you have a fragility in terms of moving from domain to domain, and you lose as well a lot of the subtleties in natural language. So for example, many NER techniques are all based upon noun phrases, which are in turn dependent on the accuracy of part of speech tagging, which is in turn dependent on the accuracy of your tagger and your stemming and the tokenizer. So you have immediately a set of error rates that compound and limit how good the entity recognition can be. So the approach that I'll be talking about, which is about 9 years in development, Dirk Van Hilft, whose name is on this, is the founder of a startup that that did this, essentially took an approach of saying, instead of looking at nouns that are in a dictionary or in a vocabulary, let's start with a small, simple vocabulary of things that are easy to recognize as this is a proper noun, morphologically, congressional and EpiPen and this kind of thing. And then look at everything else and build up things from that structure. So if you have things that are syntactic elements here, not easily identified, proper nouns, and then you look at relationships between them, resolving sort of ambiguities. Most of these are things that might be different parts of speech. But a lot of these are verb relationships as well. You can merge them into concepts which are typically noun phrases, but also have other parts of speech in them. So it's really a pretty straightforward process of starting with these syntactic elements and going through a relatively small set of rules to merge into larger concepts. And this is an example of what a rule looks like. They're different depending upon the grammar of each language, and that's a downside of a language-specific element. But for example, for English, this currently has 12 rules to cover the essentially grammatical structure and how you disambiguate what are called lex reps. One of the nice things about this is that if you get into additional attributes in the language, it's just additional disambiguation rules. So for example, adding in negation, there's no evidence of plaque in this sentence, is another rule looking for the forms of negation in language and then applying it across. Or frequency, time, measurement, these have all been added in as ambiguity rules. And if anyone here is, the next step and something that I'm working on with this group right now is to add in causal relationships and certainty. So if anyone here has done that or interested in finding causal relationships or certainty, this is very likely a connection between a disease and a medication, for example. I'd love to talk to you, so come on up after this talk. So it gives you a sense of the basic structure. And then in resolution, this uses a pretty simple matching, which is to say that if you have an ontology or a taxonomy and synonyms within that, you can simply look at supersets, sort of sliding window matches. SN here, SNOMED is essentially a medical thesaurus of terms that's standardized and quite rich. So one of the nice things in the medical domain is you do have these various resources. And picking out concepts using this sort of pattern matching bottom-up approach might provide something that's more specific, like this 7 French triple lumen central venous catheter. You said you were a clinician. Do you know what that is? Well, I certainly don't know what it is, but I know it's a type of venous catheter, and it's easy to match in these forms without doing a lot of the kind of n-gram statistics you often have in matching language. And then from matching in those taxonomies, you can provide a lot of different applications. So I've shown you very quickly an approach that's relatively simple by using, instead of focusing on building up from identified proper nouns into noun phrases, looking at the other words, disambiguating them into concepts, and then looking at the relationships between those. So you have a sense of this. One of my first questions as a newly entered manager into this is, okay, it's different. So does that matter? Is different better? So over the last about 3 months, I had folks go through and compare this to Stanford NLP using a thing called the Mimic data set. That's a, what does Mimic stand for again? It's multi-parameter something. Intelligent monitoring in intensive care. So this is a standard data set taken from intensive care transcripts in hospitals and looking comparatively at these two different techniques for NER. One is Stanford with specially trained new classes. The other is using this bottom-up technique, otherwise known as I-know. Although I met a company called I-know here, so I'm glad we've changed the name from I-know. If you look at a distribution, one of the characteristics of the Stanford NER, which comes from this aggregation approach, is you have the x-axis here is the number of words or unigrams in English versus cumulative frequency. So the red chart is the Stanford NER, and it will continue to chunk on things until you have, I've seen 16, 17 word noun phrases, which really don't exist in English. So a longer tail in terms of things considered unique concepts, many of which are actually compounds because they take out stop words like and. So things that really should be two, a 5-word and a 4-word concept are lumped together into a single 10-word concept using this classical NER technique. And this maybe gives you a sense of that. That's one of the error rates with classical techniques. And trying to honestly do the same kind of thing with this bottom-up approach, we didn't see a lot of that. We do see a lot of measures lumped in, which I hope to take advantage of going forward, but there's not a lot of things which are compound terms. Same thing in terms of what is sort of distribution. You'd like to have things where you get to a basic concept and you see it a lot, and then you can use co-occurrence to do inference and things of that sort. What we saw was that the Stanford NER approach tended to create these compound things that had ands and ors in them, and that messed up how tight the data was. The way that these compound terms work with these disambiguation rules is that both conjunctions and things like tolerated, connector words, are recognized as relationships. So these are, the jargon here is CRC, concept, relationship, concept, patterns, and on clean medical English, we see very clean patterns of these. We've also been trying this on dirty data, because all data is dirty. And that's a current area of work to make this, okay, how tolerant is this of OCR errors when you're scanning things, et cetera, et cetera. And this is, I just added this while listening to the previous talk about stop words. Although it's a bit of an eye chart, the connectors, the takeaway really here is that the connecting words of, in red, there and this, which you could consider stop words, or, there is ambiguous in terms of parts of speech, show up as concepts in a SVM trained NER like Stanford, and don't show up here. So when you see the green line dip down to 0, it means that was not identified as concept. And I won't show you the reverse kind of thing. So we scanned through on this and one other database, okay, what things were recognized by a Stanford NER and not recognized with this technique, and they pretty much all turn out to be things you don't want as concepts. Whereas the converse, things that don't get recognized in a noun phrase extractor, but do get recognized by this, are pretty good. Next is not actually something that you want as a concept, so that's an error using this approach. But at first it was like, what's a CABG? Do you know what a CABG is back there? I wrote this down because I'm not, there's all these weird terms. It's a, I forgot to write that. It's a particular kind of device for coronary bypass grafts.
One comment was
Yeah.
that, even though it's out, it might be a dozen other things.
Yeah. So there's a classical problem in NLP about what do you do with abbreviations and things of that sort. So the fact that it's recognized as a concept doesn't mean it's actually resolved as which of those CABGs this is. That's a good point. So I've given you a quick view of this sort of technique that I thought was pretty neat. And that in fact it is a little different and so far proves to be better for this kind of domain. I'll show you quickly some applications. In the medical field, there's a technique called cohort selection. You're picking a bunch of patients to take through a clinical trial, or a bunch of people that have common things to see how they worked out in a clinical application. And we have at least 4 customers and partners using this technology for cohort selection, because you can see that I'm trying to get concepts. And the basic idea is that you find concepts within doctor's notes and then set them together. One thing I've noticed so far, and I'm only 9 months in, is there's a lot of very depressing and scary terms in this stuff, because it's a lot about people dying, or a lot of the cohort selection that I've reviewed the results for is about depression, because there's a lot of depression kind of research going on right now. Northwell Health, which is a huge hospital chain in Long Island, big customer, and they're using exactly this for research recruitment. And their results are essentially a reduction in the cohort selection time from 2 hours per patient to 20 minutes per patient in review. So that's easy to measure. It's harder to measure their report that it's a higher quality cohort, but because they're looking at many more sources of information in the clinical record. There's another one that's doing a very similar thing in Brussels that just won an innovation award for doing this clinical trial management, and what they reported was that it let them reach out to a larger population and therefore get a larger number of people that meet a tighter criteria. So higher precision if you came from a search background. So the way that this works with concept selection is to identify both the concepts, as we described, and then look at co-occurrence and structure within a record to look for what are likely to be related concepts and essentially synonym detection. And then showing it to a clinician either through a classic word cloud. Apparently, depression and delusion come together a lot. Or looking at it as concepts in a timeline of how these things show up in a given patient's record over time. And then there's a variety of UIs. None of these have been built by my company. They're all people that have built them themselves on this kind of platform, looking at either these word clouds, which I used to poo-poo word clouds. It's like a nice trick, but actually I've seen so many applications that use them and use them effectively with end users, or use them in population health monitoring, where now I'm following either a concept across public health records, or I'm following this cohort over time, and this happens to be Japanese. Another application has been in, I'll say, self-evaluation within electronic health records. And I will skip this because I'm noticing I'm a little bit running out of time, but it's the same idea, just taken out to a larger set of patients, a larger amount of data, and then used in modeling for trends and evidence, and used in, they do year-end evaluations for physicians, for clinical things, and this particular group, NetSmart, has reduced their time for a year-end evaluation from 8 hours to 15 minutes. So a lot more I could talk about. This is a group that's using, essentially turning this into a search system for extraction of large patient records into single abstracts using this concept extraction. And a machine learning system that is using these things in order to predict readmission rates, stop people when they enter the ER, the emergency room, predict, are they likely to need acute care very quickly and therefore get earlier intervention. So a lot of neat applications. So let me just summarize. Hopefully gave you a taste of a bottom-up approach to this concept relationship extraction. The motivation of this was to not need domain-specific requirement and dictionaries and a lot of specialized training. I'm still discovering how robust it is against dirty data. But it definitely has found a bunch of applications in this medical domain at very high performance, and also works multilingually. If you want to know more, I'll post this deck. I'm sorry I didn't get it up before this session, but I have a bunch of pointers in there. So thank you very much.